Welcome back. So hopefully you've now had a good bit of practice using the second version of the right-hand rule to find the direction of the magnetic field generated by a straight wire. So now we're going to make a loop of wire and figure out the direction of the magnetic field. Well, we can use the right-hand rule to find the direction of the magnetic field at each side of the loop. So we have a loop with a current, and it is sort of pointing into the page here, and the current is going counterclockwise. If we look at the part of the loop that is closest to us and do the right-hand rule, well, the current is going up. So where our fingers wrap around the loop, our fingers are pointing to the left as our thumb is pointing up. As the current goes around, if we grab the top of the loop, the current is now going into the page, so our thumb points into the page, and underneath the wire, our finger will now point to the left. On the far side of the loop, now the current's going down, and if we grab the wire with our right hand, the magnetic moment is now going through the loop to the left, and at the very bottom, once again, our thumb is pointing towards us, so our finger going through the loop is pointing to the left. So the whole time, through the loop, the magnetic field is pointing the same way, to the left. If you want, you can imagine you're kind of driving a car, and if you grab the steering wheel with your right hand, if you are lazy and just drive at the 2 instead of 10 and 2, you'll notice that if you grab it, you get a good grip, your fingers are pointing towards you. Now if you keep on driving one-handed, if you turn either way, your fingers will still be pointing towards you if you keep with that same grip and you keep by using just your right hand. Alright, I'm not sure you're really supposed to drive one-handed that much, but the point is your fingers are always pointed the same way, and if you have a loop of current, the magnetic field always points that same way if the current is all in the same direction. So what does that mean? We have a loop of wire with a current going through it, and the magnetic field lines are coming out of the left side and into the right side. So we've made something like a permanent magnet. The left side is like the north magnetic pole, and the right side is like the south magnetic pole. So we make an electromagnet by making a loop of wire and putting a current through it. If we want to make it stronger, we can add a magnetic metal like iron, and the magnetic fields in the iron will align, and so you end up having a quite strong magnet that you can turn on and off at will. Okay, so this kind of brings us back to the Earth's magnetic field. We've mentioned that the Earth has a magnetic field, and we probably hand-waved its magnetic moment due to the Earth's core being made of iron. But there's a problem. So the Earth's core is very hot, too hot for iron to be a ferromagnet. So for that reason, you would not normally assume that the Earth would be magnetic. However, what happens is the Earth's core is very hot, so the core becomes ionized, it becomes charged, and because of the heat, there's like these stable convection currents of these charged ions that loop around the Earth's core. So the current, as viewed from the North Pole, is clockwise. That means the North magnetic pole points towards the South Pole, as we remember from before, and the North geographic pole is the South magnetic pole. The currents are pretty stable and they tend to stick around for thousands of years, but they do indeed sometimes flip. There's nothing kind of special about them. The direction. The magnetic field generated by the current is strengthened by the iron and nickel core, so as a result, the Earth behaves pretty much like a big magnet because of that electric current in its outer core. Okay, so to make an electromagnet, we can strengthen it by putting some iron or some other magnetic material inside of the coil. The electromagnet induces the iron into being a magnet, so it is even stronger than just the electromagnet. If we want to find the strength of the magnetic field in the center of our loop, we can adapt our Ampere's law, and we find that the magnetic field is N, the number of loops in the coil, times mu naught, so our magnetic permittivity constant, times I, the current, and divided by 2 and divided by R, the radius of the loop. So this should be pretty intuitive. The more loops you have, the larger the magnetic field, the larger the current, the larger the magnetic field. Both should be pretty reasonable. Also, the smaller you make the loop, then the smaller the radius, and so then the larger the magnetic field. So if you add loops here and have a larger and larger magnetic field, and then, if you're doing a test like is shown here, you'll be able to pick up more and more paper clips the more loops you add. Also, more intuitively, the more current you have, the more you'll be able to pick up. Another electronic device that is useful in electric circuits is a solenoid. A solenoid is a lot like our loop, except the coil is longer than it is wide. So this also acts like a magnet, and when the current goes up the far side of the loop, our thumb points up and our fingers wrap around it to the right, and then when the loop goes around, then the portion that is closest to us, so then our thumb is pointing down and our fingers point to the right through the loop. So the magnetic field points to the right, and we have ourselves another electromagnet. To be more quantitative about this, the electromagnetic, when the current flows through it, the magnetic field is the mu naught times the number of loops and divided by the length of the solenoid times the current. This is for an ideal solenoid where the it's as if it's infinitely long, but then we just take chop a certain length out of that. So we can kind of think of this as the a number of loops divided by the length is also a measure of the density of the loops. So the larger that ratio, the larger the density, then the larger the magnetic field. Also, of course, the larger the current, then the larger the field as well, so just like Ampere's law. So this device also is an inductor, and it does store magnetic energy inside of an inductor, much like how a capacitor stores energy inside of a circuit. All right, so I'm going to try another jump cut, and we're going to look at an example here where we are making electromagnets. Okay, so next we want to look at our example where we are trying to make an electromagnet with a loop of current. So in this case, first of all, I guess I should mention this is essentially always the worst question on the first exam. So the question that is something like this. And, it is kind of tricky to visualize how this works. So in this case, what I've got a bar magnet on our left here, so that's pretty straightforward, right? We've got a north pole to the left, south pole to the right, no problem. Now we have a loop of current here, and we want to know what direction is this electromagnet. So how do we visualize this? Well, first of all, this is telling us that the current closer to us is pointing up, and the current further away from us is going down. So that means we will then use our right-hand rule to figure out the direction of the current. So to make this a little bit easier, I'm going to pull out just a loop here. So I've helpfully drawn wires on it, current on it. And so what happens is, if we look at this, so the point that is closer to us is going up, and the part that is further away is going down. So what happens here? So we can put that in its place. And so what's happening? So we need to know that our right-hand rule, so our thumb is pointing up, the direction of the current, and our fingers wrap through the around in the direction of the magnetic field. So now if I put this through the coil here, so my fingers are now pointing to the left. So that means if I take this portion, basically this is telling me that the north pole is pointing to the left. Now, if I look at the backside, so this point is pointing down. So in this case, we want our thumb to point down. And so then now, if I wrap it through the coil here, so then now my fingers come out to the left as well. So in both of those cases, the north pole is pointing to the left. So we can sort of simplify this. And so this is telling us, using our right-hand rule, that our north pole here is to the left and our south pole is to the right. And so if, in this case, I think the question is asking us what happens here. So in this case, our north pole is attracting the south pole, so these will attract each other. So I think this is different from the question you have. Your job is to figure out which direction is the north pole and which is the south pole. But, and you can sort of do this with any arrangement. If we do it like this for the top loop, so then our thumb is pointing in the direction of the current, and then we wrap our fingers through, and so once again it will be pointing down here. If we loop it this way, it ends up being the same again, right? Our current is pointing to the right, we loop our fingers through, so our fingers come out of the north pole just like it did before. Okay, so this is one, I think you need to practice this a few times. It's basically just the right-hand rule, but figuring out which part is the, the part of the coil that is closer to you and which is further away. There's a little bit of sort of, 3D visualization necessary here. All right, so you have a couple questions to do, so good luck with that, and then we'll look at the forces on the wires.